Welcome to my presentation on what's necessary to establish malware freedom unconditionally. I'm Virgil Gligor. Today, I'm going to talk about the problem of establishing malware-free states unconditionally. And I'll start out as a background, defining the adversary, including persistent malware and its remote controller, and then provide an outline of a sufficient solution on the CRAM model. That's a concrete word random access machine model. Then I'll describe what's necessary for establishing malware-free states on real systems. In particular, I'll answer 4 questions about why external verifiers and challenge functions are necessary, why optimal space-time bounds are necessary for computations executed by the challenge functions, why we need these bounds for actually the code of the computations, and why these computations and the code have to be target claw free within the optimal bounds. I will end up with some question and answers, and I must admit that these questions were asked before. In particular, they were asked by some of the reviewers of this paper for this workshop. All right, the background comes from 2 papers which were published last year, which we can see on the screen. And if you like to see the proofs and of the theorems, the technical report published at Scilab contains Appendix B, which contains those proofs. So if you open up a computer, such as a laptop, what do you notice inside, in addition to the CPUs, 1 or more, system bus and random access memory? Well, what you'll notice is a bunch of controllers, such as the USB controller, a network interface card, a disk controller, a baseboard controller. And all these controllers have one thing in common. They have reflashable firmware. Of course, being reflashable, the firmware can be changed at system initialization. Now, the problem with this firmware is that it does occasionally contain persistent malware, which is either implanted by the adversary or inadvertently borrowed or loaded by the unsuspecting user. So the malware is persistent because it survives all power cycles, trusted boots and secure boots, and it does survive reflashing. In other words, if you try to run an anti-malware tool which reflashes the firmware, the malware will come back and say, done, reflashed, no problem, up to date. Secondly, this malware is placed under security monitors and anti-malware tools. So all the things that we know about security monitors and anti-malware tools at the operating system and application level do not hold here. Finally, this malware has no externally observable properties or hyper properties. And this makes life difficult because it's difficult to establish malware freedom in absence of these properties. So it turns out that this malware can be controlled remotely, and in practice has been controlled remotely by a particularly strong remote controller, as we'll see in a minute. And basically, in this case, our adversary comprises these 2 components, persistent malware and its remote controller. How powerful are these? Well, it turns out that they are very powerful. So persistent malware can extract all software secrets stored on my computer, or its computer, can modify all software and firmware at system initialization, can read and write all I/O channels and communicate with the remote controller, and can adaptively modify programs and data as it sees inputs coming. It can change the programs and data and execute any function on its chosen input. But it cannot access the processors and the storage of locally connected computers to the host computer on which malware exists. For example, it cannot access random bits stored in a connected computer to it. A remote controller can exercise all attacks, all of them, that can implant persistent malware on a remote system, including temporary, brief access to the computer, an evil-made attack. can communicate with uncontrolled persistent malware and can use unbounded computing power, and it obviously can break all complexity-based cryptography. But it cannot predict nature's throw of fair dice, namely it cannot guess or predict random bits created by quantum random number generator, and it cannot modify the hardware of the system. So with this powerful adversary, the question is how to establish the fact that the system is in a malware-free state, and how to do it unconditionally. So first, what you recall is that persistent malware has no externally observable properties or hyperproperties. Then the question arises, how can I establish the states without taking the system apart? Right? The answer is, well, what we'll do, we'll establish a slightly more powerful concept of root of trust. We establish a root of trust state, and this would imply malware freedom or a malware-free state. Root of trust means that the state of the system contains all and only chosen content by the external observer, by the external verifier. And if this is the case, automatically we know that there is no malware. However, if the root of trust establishment fails, then we know that we either detected malware or there is unaccounted content on the system, possibly caused by malware. On these controllers, there isn't that much other than the programs that are peculiar to those controllers, to the firmware, or both malware execution and unaccounted content. So with this in mind, what's an unconditional solution for root of trust establishment and therefore malware freedom? An unconditional solution has no secrets, no trusted hardware module, and no bounds on the remote adversary's power. We only need truly random bits, such as those generated by a quantum random device, of which we have plenty nowadays on the market. They're not expensive, and hardware specifications, which cannot be modified. So let's look at a sufficient solution for establishing root of trust first, and of course, by implication, malware freedom. And what you see here is actually a device comprising a CPU, which has general purpose registers and processor state registers, including registers that are set by instructions that set frequency, instructions that disable or enable interrupts, and the like. And so we have an external verifier that knows the device specifications, and it requests the system to initialize its memory. So of course, right now we don't know that the system has malware, but let's assume that the external verifier initializes the system, and it initializes it to a family of functions, CMT, which you notice here, which contain empty optimal codes, space MT time optimal code. And this optimal code is unique and target claw free. So you'll notice in a minute what target claw free is. Basically, intuitively, an instance of this is actually second preimage freedom. Target claw free means that you cannot find an arbitrary function that has a collision with a given function on some input. So arbitrary function runs on an input, a given function on some other input, possibly, and they don't collide. So, all right. So now what happens is, after initialization, the external verifier sends a nonce created from the random bits. The computation cnonce executes. If it returns the correct answer after it executes on the entire input V, which contains the memory and the processor state, and the time is T, then we know that we establish ROT, root of trust, on a malware-free device. That's basically what the protocol looks like. Now, what's the concrete word random access machine model? So first of all, this is a concrete model in the sense that it has a W-bit word constant, 2 operands per instruction, up to 2 operands per instruction, and the instruction executes in unit time. Unit time is both a blessing and a curse. It's a blessing because you only count instruction execution. We don't have to worry about latencies, and it's a curse because we cannot distinguish the instructions that we have to prove are part of an optimal program, which is a big problem. So we have to use something else. We have to use a complexity measure to distinguish between instructions which are executed in unit time. Anyway, the CRAM has no latency, no clock cycles, no frequency, no voltage, and no current, and no temperature measurements, even though a real system has such sensors. Now, the CRAM has a general architecture, general memory and words, processor registers, general processor registers, special processor registers, all addressing modes. All sorts of architecture features such as caches, translation look-aside buffer for virtual memory, pipelining, multi-core processor, hyper-threading, and the like. Most importantly, it has all the signed and unsigned instructions of a real system or a commodity system. So it has all the loads and stores and register transfer instructions, or all unconditional and conditional branches, halt, all computation instructions. That includes addition, subtraction, logic instructions, pseudo-logic instructions, shifts, rotates, variable shifts, variable rotates, multiplication, ordinary division, mod, which is division with remainder, and the like. Now, the question is, on this machine that we just defined, on this machine model that we just defined, what's a nonce and what's the computation? What do they look like? Well, so out of the random bits, the external verifier creates a nonce. It creates k random numbers, or k plus 1 random numbers, from R0 to Rk minus 1 plus x. That's our nonce. And out of this nonce, out of the k random values, it constructs coefficients Si, d plus 1 coefficients Si, out of this k random numbers, mod p, by solving this, by constructing, executing this polynomial mod p. So this SIs, these coefficients are k-independent and uniformly distributed in ZP. Now, each one of these coefficients is going to be XORed with a word out of the processor state or out of the main memory. And we construct, this is a new coefficient for a new polynomial, which is executed mod p. And this forms a family, which we call a family of randomized polynomials, and of degree d, which is one less than the size of the state vector v, which again contains all the memory and the processor state registers. On CRAM, of course, before we go into CRAM, we note that this is a k-independent, almost universal hash function. It has right properties. And on CRAM, it turns out that we can prove the optimality, the empty optimality of this family of functions. Very concretely, m plus 22 words of memory for executing the code, and t is 6k minus 4 times 6d. Extremely concretely, no asymptotics, no omegas, no o's, no big o's. Okay. And finally, this is a target claw-free family in the sense that a function f and input y do not exist such that they collide with the evaluation of a particular k-randomized polynomial on the vector v in less than the bounds, except with probability 3 over p. So this function doesn't exist. No function exists on this machine, on the CRAM, with probability less than 3 over p that has this kind of collision. That's a target claw-free family within the empty bounds. All right, now, given this, what's necessary on a real system? Well, it turns out that on a real system, we have to answer at least 4 questions, which are absolutely fundamental to the implementation of such a scheme. Again, root of trust establishment, malware-free states in reality. So the first question, 4 questions that we ask is, are external verifiers and challenge functions necessary? Secondly, can we find a concrete optimal space-time bound concretely rather than other measurements like current, frequency, voltage, temperature, energy, and so on? Third, is this bound, which is space-time, we decided by this time, is it unique for the program code, and is target for freedom within these bounds necessary? All right, let's start with the first one. external verifiers and challenge functions. Suppose that we have an untrusted system, and suppose that we connect with an external observer, which is not a trusted, trustworthy external verifiers, and there are no challenge functions that it sends. So it turns out that given that persistent malware doesn't have any properties, it's impossible to prove that the system is malware-free, the system on the right, which is untrusted. So unless we have some sort of a verification form, this is impossible for these two systems. There are no challenge functions that we can verify in any way. Okay, then let's take a look at a more general case where we have classes of protocols for n detectable properties. These protocols establish a particular property if all n systems are trustworthy, or they abort if at most n-1 system are untrusted. So for example, you have 3 systems. They don't have any detectable property because they don't have at least one of them, at least one system that's proven to be trustworthy. So essentially what happens is for these classes of protocols, you do need an external verifier and a challenge function to establish the trustworthiness of at least one component. And furthermore, that trustworthiness has to be established with a probability which is equal to or exceeds that of the property established itself. For example, the property might be unconditionally detectable Byzantine agreements for broadcast. And this might happen with probability 1 minus epsilon. Well, the external verifier has to establish malware freedom of at least one component with probability at least 1 minus epsilon. Otherwise, these protocols, by the way, will not work. These protocols are weaker or more general than the Lampert, Pease, and Shostak ordinary or traditional Byzantine agreements for broadcast. Same thing is true for unconditionally detectable Byzantine agreements for rational consensus. That is consensus of rational adversaries. And we need an external verifier that's trustworthy to establish the trustworthiness of at least one component. Otherwise, we cannot even establish traditional consensus with crashes, meaning reaching consensus on the state of the memories. All right, so now we know that we need external verifiers and challenge functions in general. So how about the space-time bounds? So the external verifier, the way it works is pretty simply, it does a baseline measurement, as you've seen before, of the result and the time on a trusted system or a simulator of a trusted system. That's basically what we did. And then the verifier compares this baseline value against the actual value that's obtained from an untrusted system. So baseline versus actual. So the baseline is always computed on a trusted system or trusted simulator. So in our case, on a real system where we have current, voltage, frequency, clock cycles, latency, temperature, and so on, we need to perform a minimum baseline measurement, which measures a minimum amount of these resources that are used by the Nonce to prevent malware from running. And we do that on this trusted simulator. So essentially, it turns out that the temperature is too flaky. A parameter is too inaccurate. Why? Because the temperature sensors may be away from the CPU, or because of ambient temperature, or because of fans. So we just set it by initialization, as you'll see in a minute, say at 37 degrees Celsius. Secondly, voltage and frequency, most of the time they're constant for most systems, but there are some which have dynamic voltage frequency, which allows variable voltage and frequency. They are linearly connected, and we set them by initialization to constant. And then what we get is we get power. We can measure the current that's drawn by the computation, by each instruction, and the constant voltage that gives us power. Frequency and clock cycle gives us time. Therefore, we are going to measure energy. That's what we do. So essentially what happens in our case, to improve or to achieve measurement accuracy at the instruction level, we have to perform a specific initialization, such as this is a measurement on one core, such as the frequency is set, the voltage is set, and of a specific type of Nonce. So that's how we initialize the system, as you'll see in a minute. So with this initialization, we can then prove that the minimum energy consumed gives us a minimum space-time bounds, which we can prove that they are the lower bounds actually. That means that we obtain the empty optimal bounds. And then the empty optimal bounds obtained do not imply necessarily the optimality of the energy, because obviously we can measure the space-time bounds, the optimality at any frequency, whereas the optimality of the energy requires a specific frequency. So the way we do it, we use the Vocaloids Model 2017 for single-core CPUs. We use their parameters. We perform a particular system initialization where some of these parameters are dropped, namely they go to 0. Others are set to constant. We perform a choice of Nonce, which enable us, for example, to make this parameter beta constant. This is the average stall time for a CPU while going to the memory to fetch a memory word. Well, in our case, it's constant because remember those coefficients, for example, those coefficients, if we use them, are computed on the processor themselves, on the registers, and then they go only once. Each coefficient goes once to the memory. Therefore, this beta becomes a constant epsilon. So with this, we simplify the formula. We notice that by the choice of integer computation Nonce, the power of the CPU and the latency for each instruction increase and decrease together. And with this, we construct our proofs that all you need is space-time bounds. You don't need energy, you don't need frequency, you don't need any of these things. A reasonable question is, how do we ensure that we get the system initialized correctly? And we do so, as you'll see in a minute, through verifiable instruction execution. All right, now, uniqueness of the bounds of the program code. Well, in CRAM, we have a unique bound. Instructions are unit times, we can get unique bounds for unique computations, whereas in a real system, we can have multiple bounds. Some bounds, which of course are computations which return the same result. Some computation bounds require a lot of memory, but very short time. Some require very little memory, a long time, and some in between. So we have multiple optimal solutions, and it turns out that we only need one, a single solution first. So for example, the verifier would request the initialization of the system to CMT, lowercase m capital T code on input U. And in fact, malware happens to perform a totally different initialization. It initializes a system. Of course, it keeps the input, for example, but it initializes a system to a different code, C capital M lowercase t, larger memory, and it initializes part of the disk with m-m. This is a matter of about 50 instructions that are written on the disk. So retrieving them at runtime is not a big deal. In fact, what's going to happen is that the computation time for this malware initialized computation is not going to be capital T, it's going to be small t plus delta t, where delta t is the time to transfer capital M minus lowercase m from the disk. And the ratio of t over small t is 1 plus delta. Delta is a value between 0 and 1 because delta is very small. And in practice, capital T over t is greater than 3. And consequently, malware beats us here. Unless, of course, we chose this computation that has minimum time and more memory. So we have to have a single choice here. Turns out that this choice has to be second preimage free because malware could modify the input during the initialization. And we want to make sure that our computation catches that. Third, malware adaptively changes code. Even code that we believe it's optimal, it can adaptively change the code based on the value of the inputs that it receives. This is a very powerful property, not noticed in the wild yet, but all the other persistent malware features have been noticed in the wild. In any case, with this, you know that we have to have code identity, and it turns out that we obtain that by introducing Nonce, the Nonce code, into the state of the memory and special purpose register itself. So it's fairly easy to do the unique code. Finally, the last property that we have is the target claw freeness in MT. So essentially what this means, as we've already discussed, is that malware cannot find within the bounds MT any arbitrary function and any arbitrary input that collides with the result, the correct result of the Nonce execution of input V on input V. So a function, arbitrary input do not exist that provide a correct reply, possibly in a shorter time than required. Also, second part of the target claw freeness in MT is that malware cannot obtain within a round trip time T the correct answer for this unbounded adversary. So malware has to block this communication and or to detect it. And once that's done, clearly we have target claw freeness within MT. And the way that's done is fairly simple in practice. It's not a big deal. We split this computation in multiple segments, which are executed random sequentially, and each segment has a smaller time than the round trip time. Consequently, a malware cannot obtain the correct result for any segment from the unbounded adversary. So how does it compare to the normal claw-free functions that we've seen in cryptography? First of all, the claw-free functions in cryptography are very similar as in this case. You have two functions out of the same family, not arbitrary functions, and they are claw-free if given a function I and an input and the result, you cannot find a function f sub j and another input xi to collide. If we are given the first function, we have target claw freeness. Otherwise, if we are not, the functions are arbitrary, you just have claw freeness. But the functions are not arbitrary. In particular, this one, fj, is not arbitrary. They have to operate in polynomial time. They use hardness conjecture and secrets. None of this are true of our function f, which is completely arbitrary. The adversary is unbounded, no hardness conjectures and no secrets. All right, so clearly these requirements are necessary in practice. Finally, the question and answers, and I'll stop here. So the first question is, how can we tell that the untrusted system is initialized correctly? What's a verifiable instruction? How do you disable registers? I mean, disable asynchronous events. So essentially the way this is done is that the computation is target claw free within MT. You include the entire vector, including the instruction that has to be executed to initialize the system and its effect. Its effect is always in a processor register. So if you include both the instruction and its effect, there is no other possibility that the malware can exercise before the function starts running. So any modification of the initialization is going to be caught. False positive and negatives, okay, zero false negatives cannot exist in ROT because the adversary can always guess, but why are they negligible? Well, it turns out that they are negligible. The probabilities are such that they are negligible, and we can always run the experiment twice, and we decrease them even further towards zero. Sure, the Sierra models has zero false positive for ROT, but what about real systems? Well, now this depends on the accuracy of the measurements that the external verifier exercises. But it turns out that the external verifier is always locally connected on the system bus, and that measurements are very accurate. Is the energy model realistic? Is there any advantage in using energy in measurements? How are the sensors protected from manipulation? Well, it turns out that the energy model is extremely realistic. As you see in the appendix of the paper, it's the most realistic model, but there is no advantage in using it. So because the baseline measurements are done on the trusted systems, there is no malware. And we saw that there is no reason to measure energy when in fact we can measure space-time. Is this paper formal enough for a productive discussion of SCS? Well, guess what? You'd have to answer that question yourself, but remember this. There is no formal model of access control. There's never been one that doesn't require secure state. There is no formal model that doesn't require trusted recovery in a secure state. And guess what? What you need for recovery in a secure state or to begin in a secure initial state, you need root of trust establishment and malware freedom. Thank you for your attention.